Today actually we start the introduction on magnetism. Now exactly what the magnetism is. The first thing, what the magnetism is. Actually, some substances temporarily or permanently acquire some property by means of which it can be aligned along the direction of the magnetic field or perpendicular to it. The property is known as magnetism, and the substance under consideration will be called a magnet. Now, at the beginning, we will try to classify magnetism. How many types of magnetism are there, and then we will move over to the reason. That is why this magnetism actually takes place. Now, first thing first, the classification of magnetism. The first one is what we know. The ferromagnet. Actually, when we talk of a magnet, we actually refer to ferromagnet. They are very strong magnets. They can attract some metals like iron, nickel, cobalt, 206. Actually, they can attract another magnet having opposite pole. Every ferromagnet or any type of magnet, it consists of two types of poles, north pole and south pole. And whenever two opposite poles come together, they attract each other. And when they are oppositely placed, that is north pole facing north same pole comes to each other, then they repel. That is the general formula. Now for ferromagnets, this force of attraction and repulsion is very strong. The susceptibility, that is the pi, that is equal to n by h, is very high. What is n? What is h? N is the magnetization acquired within the body. Now what is magnetization? Actually, we have a body and its dipole moment is capital N. Dipole moment means the pole spin into the distance. This is the dipole moment. Let us denote the dipole moment by P. When P by V is n, dipole moment per unit volume. V is the volume of the sample and P is its dipole moment. So P by V is the magnetization and H is the magnetizing field. Why this magnetic sample will be converted into magnetism? Unless it is placed in some magnetic field. So the existence of an external magnetic field is there, and that magnetic field is H, and this N, it is actually the generated magnetism within the body, that is the total dipole moment divided by total volume. So chi actually indicates that how easily you can magnetize a specimen. This H, it means the magnetizing field. Let us consider several magnetic objects and we have applied same magnetic field to them. Now, of those samples whose N is the maximum, his susceptibility will be the maximum, and whose magnetization is the least, the susceptibility will also be least for it. So actually Pi means how easily you can convert a substance into a magnet. For ferromagnets, this chi is very high. Very. Now we are coming over to second type, that is paramagnet. These paramagnets are heavily magnetized. That is, if you even place them in a very strong field, only feeble magnetism will be expected from it. Its direction is exactly in the direction of the ferromagnet, but its magnitude is very small. The susceptibility is kam, its permeability is also less. Susceptibility is very small, and the the permeability, magnetic permeability mu is also very small. Pi and mu. Now let us move over to our third type. That is the diamagnet. Now these diamagnets are also very feeble magnets, but the difference between paramagnetic substance and diamagnetic substance is such: in a magnetic field, a paramagnet is aligned along the direction of the magnetic field, and a diamagnet is placed always aligns itself to perpendicular to the magnetic field. That is the basic difference. Paramagnets and diamagnets. Ferromagnets are very strong magnets. They align in the direction of the magnetic field. Paramagnets are feeble magnets, but they also align themselves in the direction of the magnetic field. Diamagnets are also feeble magnets, and they align perpendicular to the direction of the magnetic field. That is, in both ways they are repelled. The North Pole and South Pole both are repelled by the magnetic field. So they have no other way but to stand perpendicularly in the direction of the magnetic field. Now, in our course, in our syllabus, we will not learn beyond these three types of magnets: ferromagnets, paramagnets, and diamagnets. They are included in our syllabus. But to make our discussion complete, we also mentioned that there are two other types of magnets also. Ferrimagnet. Its internal structure resembles the ferromagnets, but the ferrimagnets, it has very feeble magnetism, but of course stronger than paramagnets. And then we have our last type, antiferromagnetism. Now its structure, this 1, 4 and 5, they have the similar structure, but antiferromagnets, they do not exhibit any kind of magnetic phenomenon. But its molecular arrangements are such that it resembles a magnet. But if you try to measure its magnetization, etc., then you will see that its magnetization is zero. No magnetic dipole is ever produced by antiferromagnet. So this is our first part. How many types of magnetism is present? Now we are moving over to our second type. How this magnetism actually appears within the substance. Now it is a long story, and at the beginning I will give you only the classical picture. and I shall discuss the magnetism of these two. Then I will mention the magnetism of other types. First, the paramagnets and the diamagnets. What does that mean? How are their internal structures? You know, inside a solid, if you go to the molecular level, then you will find that several kinds of currents are there. This is the nucleus. It is positively charged, but it is not sitting idle. It is also revolving. So this nucleus also constitutes a kind of current. Nuclear spin is actually imparting some current to the nucleus, and therefore when a charge moves in a circle or in some other orbits, then it constitutes current, and whenever there is current, there is a magnetic field associated with it. So if this nucleus gives rise to some magnetic field, then of course the observer will understand that this nucleus is magnetized. It is not really. Actually, it is the spin that causes the current, and therefore this current constitutes the magnetic field, and to an observer at a long distance he will feel that, well, inside the nucleus there is a magnet. So whenever there is some magnetic field, I have some moment, dipole moment. If we denote dipole moment by mu, then mu is equal to, because you know that nucleus is rotating, as I have just explained to you, that nucleus is rotating, therefore it gives rise to some magnetic field, and it will appear that this nucleus as it has some magnetic moment. Now our next current is the atomic electron. These atomic electrons, they revolve around the nucleus in circular or elliptical orbits, so it constitutes some kind of current, and therefore it gives rise to some magnetic moment. I have designated this by mu orbit, that is the orbital electrons. They constantly revolve around the nucleus. They may not be in the circular orbit, they may be in the elliptic orbit, but in all the cases, this moving charge, this moving electron, it constitutes a current. And whenever I have a current inside a loop, then according to Ampere's theorem, if I look from outside, I will think that, well, there is some magnetic field. And where does the magnetic field will come? Of course, this orbital motion, it resembles some kind of magnet, as if a magnet is there, and this magnet is supplying the magnetic field. Therefore, I have this mu orbit, dipole moment due to this motion. And thirdly, this electron has some spin. Actually, it is rotating around the nucleus. So this also constitutes some kind of current, and this current is mu spin. So for a magnet, for an atom, these are the three sources of magnetic dipole moment. Okay. One is the due to orbital motion, one is due to the spin motion, and the third one is nuclear motion. Now these two are sufficiently higher, whereas the contribution due to nucleus is very small, rather very small. So for the first approximation, I can neglect. If you like, you can add some vector sign over it. So this is your magnetic origin. Now, from the magnetic, from the atomic source of magnetism, I can deduce something classically and quantumically. Let us move over to it. Let us assume that this electron, it has some linear velocity v. Then how many revolutions it will make per second? V means how much distance it will move in 1 second, and the length of the perimeter of this circular orbit is twice pi r. So how many times the electron will move in 1 second? This is equal to F divided by V divided by 2 pi. This will be called the frequency mu, that is equal to omega by 2 pi, where omega is the angular velocity. I think you have understood what I am trying to say. This electron, it moves a distance v in 1 second. And if the length of the orbit is 2 pi r, then for each 2 pi r, it moves at a particular point. Say I have a cross section here, and the electron moves once if it moves 2 pi r. If it moves 4 pi r, it will cross the cross section twice. So if it has velocity v, then the frequency will be twice v by twice pi, and that is equal to omega by 2 pi. So this current, it constitutes this thing, it constitutes a current. This current will be given by E omega by 2 pi. Just try to understand why. What is the definition of current? Definition of current is, you put one cross section here, the amount of charge passing per second will be the current. Now, how much charge will cross it per second? This electron, it has a charge E, and it moves omega by 2 pi times in 1 second. So obviously, omega by 2 pi times a charge of magnitude E crosses the cross section. So what is the current? Current is the total charge passing through a cross section in unit time, that is in 1 second. So this is the number of times the electron moves through the cross section, and in each time it has charge E. So the total amount of charge that crosses the cross section is E omega by 2 pi. So now I know what to write, and there is a this circular path, it actually constitutes a magnetic dipole. This magnetic dipole moment, the moment of the dipole moment is mu orbit, or rather O at its side, that is equal to I into Q. Ampere cell theory. That is, if you have a loop and a current passes through it, then obviously you may assume that it is equivalent to some magnet whose boundary coincides with the boundary of the loop. Here also we have the same condition. We may consider a magnetic dipole here, whose dipole moment is I times area. That is, I am putting the values of I and A. I is E omega by 2 pi and A equals to pi into R square. So these two pi's will be cancelled out. This pi and this pi, it will be cancelled out. So it will be E omega R square by 2 half. That is the value for mu O, O for orbital motion. Now, what is the angular momentum of the electron? If it moves round the circle, this electron has mass m, so angular momentum L will be equal to LVR or small l rather, this is equal to LVR. Now V equals to omega, so it is equal to N omega square R. Okay. N omega one is L equals to MVR, P cross R, P into R. Now V equals to omega, V equals to omega into R. So this is the angular momentum. Now if I place it here, then this will be equal to half 1 by 3m into E into m omega R square. So actually this is equal to E by twice m into m. That is the magnetic moment associated with the orbital motion. Now, if I move over from classical mechanics, theory to quantum theory, then obviously we will see that L cannot have continuous value. Its value is quantized. You know the diagram, the famous diagram for L. This is the LZ. And we have this origin O. Now let us consider we have L equals to C. Then the Z component of L will be Nl equals to Q1, 0, -1 and then -2. This is 5 value. Classically, if I observe this diagram, then we will see that when L equals to 2, so it can be oriented at any angle. Infinite number of orientations are possible. So Lz has a continuous value from +2 to -2. Every possible value is in +2 and -2. This is Lz equals to +2, this is Lz equals to -2 because L equals to 2. So this length is also 2, this length is also 2. Now, According to quantum theory, for this line, ML equals to 0. Because if you draw a perpendicular, then it will pass to the center. So it's ML is 0. Then we have equal angle. This angle should be equal. This is for ML equals to 1. And this is for ML equals to 2. So you can see that no atom will be able to be aligned in this direction. This ML equals to 2 is the maximum angle it can move. Similarly, if I move downward direction, then we will have here ML equals to minus 1. Here we have ML equals to minus 2. So what does the diagram actually signify? It signifies that say we have magnetic field like this. This is the direction of the magnetic field, and we are talking of some atom, or rather the orbit of an atom. Let us consider an orbit like this. So its angular momentum will be like this. This angular momentum vector will precess round the magnetic field. It will move. This vector, this angular momentum vector will move along this. So the orbit will over, when it is in this position, its orbit will be perpendicular to it, it will be like this. So keeping this point fixed, the orbit will move, orbit will rotate, so that its angular momentum vector of the perpendicular normal passing through the center, it also rotates in a circle. Now for this circle, if I draw perpendicular, as I have drawn here, its z component of the angular momentum will be given by ML. Its value is plus 2, plus 1, 0, minus 1 and minus 2. This 5 values is provided if L equals to 2. If L equals to 1, then its ML will be minus 1, 0, plus 1. So now I think you have understood that well, mu equals to mu orbital equals to E by 2m into L. This is alright, but not all the values of L are permissible. We are trying to find out what is that harmonium. This mu real mu rather it is related to angular momentum. So it will be minus E by 2m, and for L angular momentum it will be L h cut by 2 pi. L h cut or h by 2 pi. H cut means h by 2 pi. So that is the value for the uh, or magnetic moment due to magnetic moment of what? Of an atom due to the presence of the magnetic field. But you know from your early quantum mechanics classes that these L values, they are present even in the absence of magnetic field also. The magnetic field is not there, but these energy values are true. So this orbital motion of the electron, it gives rise to some magnetic moment, and the magnetic moment, dipole moment will be given by minus e by twice n into L h squared by 2 pi. L h by 2 pi, or it is L h squared. Now this thing we can, I think we can write it properly. That is equal to minus mu b into L. Where mu b will be called the Bohr magneton, and its value is E h squared by 2m. It is Bohr magneton, and its value I am writing it here. You will have to memorize it. Its value is mu b. Its value is 9.27 into 10 to the power minus 24 ampere meter square. This is the value for the Bohr magneton. So whenever you will see that an atom is the electrons inside the atom are rotating in elliptic or circular orbit, then just remember that it amounts to some magnetic field, and the magnetic dipole associated with this circular motion or elliptic motion is equivalent to a magnet whose dipole moment is given by mu equals to minus mu b into L, where mu b is called Bohr magneton. Its value I have written there, 9.27 into 10 to the power minus 24 ampere meter square, not per meter square, ampere into meter square. So if I put the values of L, then it will be L minus mu b L, then minus mu b L minus 1, then it will be minus mu b L minus 2, etc. Now similarly, as I have told you, this new orbit and this spin angular momentum, they are more or less same type. Only difference is mu s equals to E h cut by n into s. Next. That is the value for the mu s, and it is actually, if I write it in symbol, then it will be uh, you can see that its value is half of this one. You must remember the fact. Whenever you are moving over to spin angular momentum, then you will have half of this. Actually, I cannot prove it classically. It needs quantum mechanical treatment to prove that this mu h is E h cut by twice mml. This is mu h equals to E h cut by m into ml. There is a two factor needed. Now we can move over to next section. Nuclear magnetic motion. I told you that I will neglect it because it is very small in comparison to everything. The eigenvalue of, and I must tell you that these two angular momentum, they are actually coupled. In the so-called LS coupling, the total angular momentum A equals to L plus E. If you try to find the eigenvalue of capital J, then it will be eigenvalue of capital J will be H over V into V plus 1 into H. Always remember this type of expression, because when I am trying to find it classically, then it will be equal to J h. And when we are trying to find it quantum mechanically, then we have J into J plus 1 into. Now I think this part I have explained to you, and then we have this susceptibility. Let me just give you a few lines to prove this. Let me clear this board. Now we will have some first-hand experience of some quantities which are fundamental in the case of magnetism. At the beginning, we will consider two types of magnetic field, B and H, and this B equals to mu naught into H for non-magnetic media. These B and H are external magnetic fields, and mu naught is the permeability of the field. Mu naught, the value of mu naught equals to 4 pi into 10 to the minus 7. This Henry per meter. The unit of H and D, they are the unit of H is ampere per meter. If I have some magnetic material, something other than air, then I will have the relation B equals to mu into A, where mu is a constant or the permeability of the substance. But you must know that this mu, it is a very complicated. So I can write mu equals to mu r into mu naught, where r is the relative permeability. Mu 0 is the permeability of the free space, and I have total magnetic moment is mu. So mu equals to mu r into mu. Mu r is a very quantity that we can introduce. Its value you can memorize. Now we may relate this B and H by some relation. B equals to mu naught n plus H. What is the meaning of this line? Say I have one magnetic material and I have magnetic field. The field strength is capital H, and here you have magnetization, and this magnetization, that is dipole moment per unit value, it is capital M. So it also gives rise to some magnetic field, which will be denoted by some lines in the opposite direction to that of the external lines we have here. And also capital M equals to pi into H. So if I put it here, then mu H, D is mu H, so it is mu H equals to mu naught n plus H. So take the scalar value of it, we are forgetting that they are vectors. Now if I divide n by h, then what we will get? Here we are dividing the whole expression by h. So mu equals to mu naught n by h plus 1. Therefore, this expression may be written as mu by mu naught equals to n by h plus 1. So what is n by h? Mu minus mu naught minus. Therefore, chi, that is equal to n by h, that is equal to mu r minus 1. You know that mu by mu naught is mu r, some distribution. So it is the value for chi. Okay, that is all about the preliminary topic. So we can stop here and